right, everyone. Thanks for coming. This is the streaming schema, drift discovery, and controlled mitigation. It's kind of a mouthful. Assume if you're here, you've either experienced this problem or you don't know which way the Gucci session is. So, well, the timing was perfect on that one. All right, let's get started. So, who am I? Just real quick. I've been doing software engineering, data engineering, ML engineering, all the engineering buzzwords for a while now. I actually started doing pen testing, which was pretty cool, where we try to hack into these huge networks. That was fun, but then I moved to software development. Started doing big data when big data was hot, MapReduce on-prem. If you guys have ever done that, you know what I'm talking about. It was a wave. Then everything shifted to the cloud, and we have some really cool capabilities, cloud-native MapReduce and all kinds of good stuff like Databricks. And at that time, I was one of the first, if not the first, Databricks professional services person. So I worked for Databricks on behalf of them, but not technically paid by them. So that was pretty cool. Got to meet a bunch of cool people who wrote Delta and all that stuff, and I got to talk to them. Right now, I'm doing consulting for a very big retail company, petabyte scale problems, which I was a little intimidated by at first because it's a lot of data. And I'm a big fan of computer science, algorithms, data structures. I love music. I love listening to music. I love playing music. And I like memes. So the meme one is near and dear to my heart. You're going to see this very soon. So just to set the stage of, what is the purpose of this, instead of just diving into some ultra dry talk about schema evolution. So really, everything that motivates me is not to get called when production is broken. That's everything I do somehow originates from that goal, right? So if it's my job to create the ingest pipelines that are serving analytics, BI, ML, there's a lot of people who can be angry at you at any given moment. So I support incident response. I support the ML team. I support team doing BI, as I said. And any one of them at any point could say, this data doesn't look the way I thought it's supposed to look, and hate you, right? That's kind of what you want to avoid. So this is the scenario right here that I put. So incident response, they often have very time-sensitive queries. And they don't talk to you for maybe 2 weeks until there's an incident, and then that you need them right now. They need you right now. So what you want to prevent is them saying, I want to make a query, I want to answer a question, but I can't because when I went to the table that I thought was my data product for this question, I didn't see what I needed. Right? The key I needed wasn't there. Where is it? Why isn't it there? So that's kind of the nightmare scenario. So this brings up schema drift. Right? Schema drift, in a nutshell, is you thought you solved the data modeling problem. You thought you nailed it. And then tomorrow comes, and you realize that it actually changed without you even noticing. So it's a difficult problem to have. I actually didn't even experience this problem for a long time because I had relatively stable upstream data providers. Sometimes those data providers were giving me really nice contracts too, like protobuf contracts, which are, like ironclad. And that's nice. If you're in that situation, man, God bless you. But sometimes these data providers, they'll give you JSON data, and they want you to be grateful for it. So you get JSON data, and I'm just going to pick on JSON data because it's so popular with the security vendors that I'm using. And JSON, when you really think about what JSON actually is, it's just a map of string to any, right? So you could have a really nice case of string to string, and everything's great, and that's all you have. But you can also have string to nested object. In your nested object, you can have an array of nested objects, and the nightmare just unfolds right before your eyes, just like watching a train crash. So if you've experienced these wonderful data sources, this talk is for you, right? Yeah, and the last bullet, just to drive it home, the vendors don't talk to you, right? They're just going to release their data. They're going to do what they do, and you have to deal with it. So I love this slide. So the data providers are ready. They will move the goalpost. Are you ready? Because you're going to kick it, and you're going to miss, right? So if you guys have tried to solve this problem, you've probably seen within Delta merge schema. Merge schema is awesome, right? It does a certain set of things really well. Should you just use merge schema to solve your schema evolution problems? Well, you could, right? Merge schema is like parking your bus on the train tracks. Maybe the train will never come. It's possible. Maybe the train was decommissioned, you know, whatever, but if it wasn't, you're going to have a bad day. So I've had a bad day, just like that. The thing is, you're putting a lot of trust in merge schema if you choose to use that as your primary mechanism for schema evolution. And the reason is, the things that it can do, for instance, it can fairly easily add new columns to your data frame, to your delta table, excuse me. It can do that no problem. But if you just say, do that in all circumstances, in all cases, you run the risk of having 10 columns today turn into 100 columns tomorrow, turn into 1,000 columns the day after that. It's basically an unbounded set at that point. So you really, unless you know for a fact that the train is not coming, I wouldn't do it. So I think there should be some kind of a gating process where a human or maybe something very smart can say, yeah, this is going to be appropriate or this is not going to be appropriate. So I've seen, just to give you a couple of examples, I should have put some on the screen, but a couple examples would be the data provider had a section within their JSON events that any developer could write anything they wanted inside of it. Right? It was just a free-for-all. So it was, the subtree was something like debug context. So first of all, you'll hear me talk about trees a lot, because when I think of JSON, that's basically all I think about are trees, where the root of the tree has the children of the top-level fields. So if there were 6 top-level fields, there would be 6 children, right? And then the tree just kind of goes out forever as much as it needs to. So they had a subtree where they're just like, you know what? We're going to put anything we want in here. And the developers were totally unconstrained, and they did just that. So, you know, as a data engineer, when you see this, you have to ask yourself, one, is there even a business value to this data, right? That's a big question, because I know that even though we're developing bronze layers, potentially, this is the focus of what I'm going to be talking about, and you want to keep the data as pure as you can, there comes a point where it may borderline be abuse on the data providers of what you're trying to accommodate, right? So you don't, in my opinion, you don't want to support that, even though in general you want to take as much as you can. All right, so I've seen dynamically generated keys. That's a good one too, where literally the keys will have UUIDs in them. And they're just changing. You know, Eventum is like, who thought this was a good idea? Like, who designed this? I wish I was kidding, folks. All right, so the next question is, how about schema evolution within autoloader? So I'm talking about streaming a lot. I love autoloader. Remember before autoloader is a pain in the butt. So just a quick recap on autoloader and why I love it and why we're onto something is because with autoloader, you can say, hey, I know that I'm going to have S3 files or whatever you know, distributed object store you have. I'm going to have files coming in, right? And I know that I can make notifications that reflect something has happened. And I know that I can hook up Spark to basically a queue data structure to say, hey, an event came in, there's a new file, Spark go find that file, Spark go process that file. So autoloader makes this so simple. And what they also do is they give you schema evolution strategies that you can use. So a lot of what I do, all of what I do is really built on the back of what Databricks has done. So you know, Databricks has amazing engineers, they're aware of what the problems are, and they're innovating to solve it. So they got pretty far, and I'm happy what they had. So the question is, for my specific use case, what did I actually need? Well, my customer told me that he wanted to make sure that bad records, like records that couldn't be parsed because they were not formatted well JSON or whatever the problem was, he wanted them isolated into a location where he could look at them later. So, you know, classic bad records path, right? Turns out bad records path doesn't play well with some of the autoloader schema evolution strategies. So that immediately eliminated some of the options that I had available to me. And the other thing is, what if we don't want to add all the new columns to our table, right? Like I said, some of these columns are like just hot garbage. You know, you put them in there at your own risk. So there are evolution strategies that will just take them. They're basically an extension of the merge schema true philosophy, right? So that's probably not what you want either. And for my use case in particular, we want to make sure that the streams are not going down, right? Because these streams are pumping use cases, and these use cases, they can't stop, right? So downtime is very bad, and we want to minimize it at all costs. So what does that leave us with strategy for autoloader? That leaves us really with one strategy left, and that's the rescue strategy. The rescue strategy is very, very nice, and mostly because if you think about it, what Databricks has done is, and this is what I am doing also, if you have a large number of data sources, and let's just say they're JSON for simplicity, You need to onboard all these data sources. And simplicity really is paramount because you have to maintain all this software. Anyone who's put software in production knows the more complicated your stuff is, the worse the time you're going to have in production trying to figure out what's wrong with everything. So simplicity is always paramount, number one. So if we can use the built-in JSON schema inference to figure out generally what our schema should be as a starting point, that's a big win, right? So just a quick recap of what that is. So what happens is you specify a location where all of your data is. And there's a certain amount of files that are sampled within that location, which is configurable. And it will basically look at every single JSON event that you gave it in every single file. And every single record will have a schema that it will figure out. So if you look at all of the schemas for every single record in a file, it consolidates that into one master set. And it does this n times across all of your files, and then smushes all of them together. And it's like, bam, there's your schema, right? So it works really well for a lot of cases. Now, what it doesn't work well in is when you have things like sparsely populated data, right? Because there are keys that you might not even find because they're so rare. It's like, where are these keys coming from? Like, check under your seat. There might be one under there. Like, I don't know where these things are coming from. So back to the rescue data. The rescue data is actually comparing the schema that it first essentially initialized with the current micro batch that is happening in real life, right? So if it sees something that conflicts with what it expects correctness to be, it'll populate the rescue data column. And that that column is of type string. And that's serialized, well-formed JSON data. So it's pretty big. We used to do this as the RSA role manually back in the day, and I don't recommend that, just as FYI. So here's an example of what actually would be in that column. So it would be a string where it would have key, whatever the key was, and the literal value. It would actually just be there for that record. So if you got an event, and the event had, I know this is a silly example, but if the event had a key of key and a value of value, you would see that in the rescue column because it didn't match up to the initialized data. So this is amazing, right? Now you know exactly what's missing. So clearly it's like the wheels are turning. There's got to be something we can do with this, right? I mean, they've gone so far. I should be able to take the ball now and finish this and close. So that brings us to drift detection implementation, if you will. So since we know that every single rescue data value is well-formatted JSON, what can we do with this, right? There's got to be something we can do with this. So one idea is to just create a vectorized UDF to analyze that JSON value, right? I call it tokenization. I feel like fundamentally that's not right, but you'll hear me say it all the time. So I create a table to capture the knowledge of schema drift. So let me just run through what this table looks like. So every event has an event origination timestamp. The event date is just a truncated version of that, right? That's useful for partitioning and querying and nothing much more than that. So what I also wanted to make sure that schema drift was quantifiable in a given time window, right? Because let's say I care about the last hour or the last 2 hours. I want to be able to make sure I can ask questions in the context of time, like most people want to do. So the tokens are actually the things that we care the most about. These are the things that we've uncovered that we weren't expecting. And if you think about this as a tree data structure problem, really what this is you're traversing the subtree from the node that's new all the way to the bottom. Sorry, the root node all the way to the bottom of the node that's new. So in this case, you can see I have an actual JSON example. So the key is ABC, right? And the value is of type object. So this is one of those nested cases. And then inside your nested object, you have a key called def, right? I don't know why I use such stupid names here, but this is what we have, folks. So what you would actually see is a string in that array, because it's of type array of string. You would see abc.def, right? And you would have all of these for every single thing, for every single record, for every single table. I implemented this across all of our bronze tables. And we have over 50 and growing every single day. And now on to the things that really give you even more value. What can you tell me about metrics? How can we quantify this in terms of how prevalent is this? How bad is this? So you have things like average new keys per record, because you have to keep in mind that every single record is going to have a different amount of schema drift. It's kind of a weird concept, right? It's not like a file or it's not even a micro batch. It's literally every event. So you have to really think about it in terms of events. So this is just telling you, well, across all my events, the average number of new keys is blank, right? And the max number of new keys. So maybe there was an event that came in that had like 500 keys in it, right? You know, that could be well above the standard deviation or like 10 times standard deviation, right? We don't even know. But those are interesting because those are the ones that I would harp on, and I'd bring that to business, and I'd be like, what are all these keys? And that's when you have a nice tight feedback loop with business and with analysts who will guide you and tell you whether or not these things are valuable or whether these things are what I like to call space junk, you know, just debris you got to watch out for when you launch your rockets. And then total new keys. That's just the number of keys aggregated. So do I have to manually query that table? Of course not. Come on, people. Let's get real. So back in the day, before Databricks acquired Redash, you guys probably remember, all you could do was use these like really cheesy inline visualizations. Those were the funniest times. So you know, you couldn't really make a good dashboard with that. I know they tried, you know, they had a little feature, but it was horrible. Right, so I used to have to export that into a proper dashboard technology. But now with SQL Workspace, I would say they closed the gap by like 95%. So it's really not worth it, in my opinion, to leave the platform. The platform has evolved to the point where it's just so good at everything. It's almost like not even fair. So I like to use SQL Workspace in order to power a dashboard that's based on the underlying table I just showed you. So yeah, let's create some visualizations. Let's do this thing. And what I like, too, about SQL Workspace is you can also create alerts on arbitrary queries. So if you wanted to set a number and you wanted to take a hard line on if I see more than 10 new keys in a given window of time, I'm going to alert the system or the operations person at the time, right? Because this, to me, means we are significantly departing from what we thought this should be, right? And we don't want, the key thing to remember is we don't want our customers ever to tell us something that we didn't know. Like that's fundamentally my opinion, right? Because then, at least for me, I feel like it gives you a bad rap, and the people lose confidence in you because they feel like they're telling you something that you should already know. So I always, always, always try to be one step ahead, at least, of the people consuming my data products. And actually, before I go to this, so a very, very quick tangent. It's related to creating good alerts and good triggers. So you can ask yourself, how do I create a good trigger to alert on schema drift? That's a hard question, as it turns out, to ask, because depending on the data source, you'll have widely different answers. So Okta, I'll give you a perfect example. Okta is the one that does all the shenanigans with the metadata dumpster store, essentially, where they can put anything they want, and there's literally hundreds of developer put key values that have no value to anyone. So in that case, a large number of drift is expected. Now that is even harder of a problem to solve because now you're looking for the needle in the haystack because you see all this space junk and you still have to find the good one. So what I like to do, and I've been doing this for a while now, I like to build time series models for each data source and each metric, right? So if you think about some of these metrics, schema drift, the number of average keys per record is a perfect metric that you could do this on, or total number of keys, any of these numerical values that are aggregated. So you can train a model to learn exactly what is normal for this specific metric for this specific data source. And then what you could do is you can get alerts that have transparent scores to them. So you can get a severity score between, let's say, 1 and 5. Maybe you get a 5 severity score. It goes so far as to say, I gave it a 5 because it's 100x larger than what it's normally. So it's literally that level of information. And one example of how you could do this is with Elasticsearch time series. I have no affiliation with them at all, but I'm just saying there's lots of ways you could do it, and that's one of them. All right. So these are actually screenshots from the dashboard, but I put a video together after the fact. So let's look at the video, which is the actual dashboard, instead of showing you screenshots of a dashboard. So just to set the stage, schema drift discovery is just one component in a healthy ingress pipeline. There's lots of things, right? You can't focus on any one thing. There's lots of dimensions to this. So I have a single page, single dashboard, where it shows all the dimensions that I think are the most important for a healthy production pipeline. So in this example, you'll see we have two main parameters that drive the dashboard, which is just going to be your time range and your sources. So all of our bronze sources are cataloged with certain bits of metadata, so we can easily identify them, route them, do whatever we need to do with them. So you're just going to see here, you can see I got a bunch of them. This is a real thing. So we're just going to use box in O365. So the first thing we want to look at, latency, right? What's my latency? So some latency comes from upstream, nothing you can do about it, but you still want to know what it is, and you still want to see where it's trending. So that's what the latency is showing. All right, and O365 actually has 3 subtypes. So if you were wondering why it exploded, it's because of that. This is useful too. I mean, this shows what are the outliers. Outliers are sometimes important, sometimes they're not important, right? Sometimes the reason you have an outlier is because the forwarder that sent the machine was down and it sent it super late. And that's why it was a lot of latency. But volume is another critical aspect in production monitoring, in my opinion. So this is part of that too. I promise we're going to get to schema evolution at the bottom here. So yeah, again, any one of these individual metrics can be sent into time series machine learning models to do anomaly detection. And I think that's, in my opinion, that's the pinnacle of alert discovery that I've ever done. This is showing information about the queues, because obviously we're using autoloader. Autoloader's using SQS queues, at least in AWS. Go on. Past Alex is going a little slow right now. And there's schema drift at the bottom. It's coming. Making us wait. There we go. So this is showing over time schema drift for box and collectively O365. Again, O365 is 3 actual data sources tied into it. But you can see, exactly what's going on with these data sources, whether they're trending up and down. In this case, you can see that they're relatively stabilized, and that's because I've already addressed the biggest problems, because this is in production. So here's a good example. Let me just pause this for a second. Oops. Yep, right there. So this is a good example because you can see the magnitude by frequency. I know word clouds are not generally that interesting, but I like them for this use case, believe it or not. You can see something like additional underscore details dot shield alert, like all that random stuff. That would probably be space junk. You could tell just by looking at it that no analyst is ever going to query that. But something like, let me see if I can find it. Browser version, right? That could be legitimate, right? Why isn't browser version a first-class citizen in the Delta table, right? This is the question that we should be asking ourselves as data engineers. Did I capture the data as necessary for business to use appropriately? So this is in here. We also have kind of a stripped down version, arguably the most important details. So you can see what the table is, the actual table that originated this problem. You can see the token, and you can see the number of occurrences within a window. So you can see, and it spans multiple data sources, right? So this is for every single data source. We solve the problem exactly the same way every time. We minimize complexity, because nobody wants complexity, and it works. It just works, right? And these are Spark metrics. So just a quick FYI, if you want to get Spark metrics, you can implement a listener, which is really nice. It's actually what Databricks does to give you some of the fancy stuff that you see when you're in a notebook. But you can do the same thing that they do and implement a streaming query listener either in Python or Scala. And then you can send those anywhere you want. That's what I did, and now that I have them here. All right, and we're back. Let's see if I can get this going here. Perfect. Controlled mitigation. Is this clickbait? I don't know. Not really. Maybe a little bit, but not really. So let's say we've been monitoring the dashboard. We have either manually looked at the dashboard and made a determination, or we have a fancy trigger that told us, hey man, wake up, things are bad. Either way, so now we're thinking, well, we want to promote the keys that business has told us that they need to be there, right? And we also don't want to promote the junk. So like debug context.star is one of my favorite for things that just never should make it into any Delta table ever. So in order to do this, we need to go back to autoloader. It's coming around, full circle. So like I explained earlier, the schema inference process is happening when you first start your stream. It'll look and it'll say, hey, did I do this yet? And it does that by seeing if there's a file. So that's what Databricks actually does, in case you're wondering. When they're doing schema evolution, they're writing metadata to a file. And if you look at that file, what it actually is just a stringified, essentially a stringified struct type, right? It's literally a struct, like object that you could look at in any language, stringified with some additional metadata that they put in and a couple magic bytes. That's basically all it is. So they have a version in there to make sure that they're compatible with what they're doing. And that's kind of all it is. So we want to make sure that we're looking at that. We want to make sure we're utilizing that. But we actually can't promote any keys to our Delta table because it's stopping us, right, by design. By design, it's not letting in some of the things that we found. Because we can't just, I don't know if I covered this well, but we can't just let everything in, right? So although we want something now, it was wise to not let everything in because there's plenty of stuff we didn't want. So we need to be the gatekeepers of this. So now the question is, well, autoloader is doing what it should be doing, but not quite what we want. So now how do we go? We're like so close. We're so close. How do we go to the rest of the way here? Come on, autoloader. Reverse engineer it, obviously, right? We've got to do it. Sometimes it just feels right. So yeah, looking at, I already said this, it's stringified. Like, if you'd be amazed, it's literally a stringified struct type. So a quick refresher of what these struct types are. When you're talking about schemas, in any sense of the word in Spark, you're talking about struct types, right? Struct types are like, they're like the umbrella for all this. Within a struct type, you have struct fields, right? That's really all you need to know. But they just like JSON, they nest uncontrollably. I don't know if you guys have ever seen the old code where they have like 8 indentations deep of struct type definitions. Only data engineers can appreciate that pain. So what do we do? What do we do? We're getting closer and closer and closer. We understand what schema evolution is trying to do from Databricks. We appreciate what they're doing. We just need a little bit of flexibility, right? So how about we write a simple Python library? And all the Python library will do is it will read the file that Databricks created, right? It'll load up the data. It'll unmarshal it. It'll put it back into memory as an actual struct type, not as a string, which we can't work with. And then let's get a really, really simple public interface where all that we let people do is add to that in the same way that we've added to it for years. So nothing new. The whole idea was to make sure that this API is something very, very familiar to every single Spark developer out there. So if you've ever, say, add field somewhere, right? Or if you ever made a call where you put an array and then you put an array of struct fields, it's just like that. It's exactly the same. That's what the whole API is based on. So we can represent arbitrarily complex data structures now, not because I'm some kind of like software genius, but it's because that's what it already could do. That's what already could happen in struct types. So I'm really, as much as I can, I'm just letting Databricks carry me to victory, right? Because you don't want to do too much of this work yourself. So when we're done adding the fields, the new fields, naturally, we would want to overwrite that file. And why do we want to overwrite the file? Well, it's because the next time we get a micro batch, just like what was happening before, schema evolution is going to look at that file, and it's going to compare the contents of that file with the contents that we currently have in our micro batch. But now, it's going to say, oh, yeah, that's OK. You're good. I'm not going to put that anywhere. That should have been here. But there's still one problem left. I'm kind of rushing myself. That's OK. There's still one problem left, and that is Delta is not going to let it in. All right? So we've gotten halfway there, but now Delta's going to say, ooh, what are you doing? This isn't right. Delta's going to say, this is a schema mismatch, buddy. I'm not putting that in there. So now we have to deal with that problem. So the operational impact, just to kind of tie this in together, how do we actually update that file? We have to stop this stream. So there is maybe a minute of downtime, maybe a minute. So you can alleviate this even more by using pools. So it'll keep them warm for you. You don't have to go out and get the instance again. It'll be ready. It'll be much, much faster. So that's what we do. So I also have a template of this. I call it a migration, a schema migration, because I'm used to those terms from other realms. But when we want to do this schema migration, all we have to do is use a template notebook that I've created. It has the code from the library. You can see exactly how I'm doing it. And I'm going to share that too so you guys can see that. The notebook takes, like a minute to run, because again, it's just reading from a file, writing to the file, and that's it. I mean, that's all it does. It's not particularly exciting. So we have to go back to merge schema. Ironically, I'm just hating on it, and now here we are again. So I know this will sound like maybe I'm contradicting myself, but merge schema true makes total sense now. And that's because we put a gate in front of it. So that was the key thing missing. So now merge schema and autoloader schema evolution are working in tandem and are separating the responsibilities of schema evolution in such a way that is much, much, much more controllable and much, much more robust, right? So before I do a conclusion, let's go to the notebook so that we can actually see what it looks like to do this migration. It looks like I'm running a little low on time, so I'll speed through it. So this would be the schema migration notebook. I think I might manually advance this a bit. So this is just telling you, hey, this is a notebook you should use because I've already solved this problem. So use this notebook and just modify it a little bit. So all this is doing is it's getting the library that I told you about. It's installing it. Nothing exciting there. To run this notebook, you're typically going to give it a table name and the schema location for autoloader, wherever that schema that I told you about, that internal file. You can tell it where that is and where the table is. And then it's going to be able to help you overwrite it. But the first thing you want to do, maybe this is from paranoia, I don't know. But I will always manually look at the values, the schema drift values. I know I saw it in the dashboard. I know I got a trigger, but I'm just that way. So I go through this, I look at it, I see, okay, rescue data has all that. So you can see actual rescue data right there. That's what you would see in the column. You can see it's well-defined JSON. I was like, okay. I see the tokens. Okay, yeah, some of these tokens I want. And in this example, just for simplicity, I am going to promote them all, but I could just as easily have not done that. You'll see I'm just going to do a loop, but I could just as easily have not done a loop. So there's not like not any snake oil or anything. These are the new tokens, and this is going to be important. You'll see in a second. Come on, past Alex. Let's get this over with. There we go. So what I'm doing now is, I'm going to pause here. What I'm doing now is I'm saying, okay, I need you, Spark, to help me once again. I need you to run your awesome JSON schema inference engine on all of my rescue data strings. So this is a neat little trick to bootstrap the whole process of figuring out how I'm going to overwrite that file, right? So if you look, you can see I'm going down into RDDs, and then now if you look, I'm looking, these are the actual, the new keys that I want in my data frame, in my delta table, excuse me. I like that bottom text there. Copy the schema in case we screw something up. It's cheeky, but we do. We screw stuff up. So you should obviously always back up the file. I mean, that file's critical. It would be like messing with checkpoints and then not backing them up, right? So you make sure you back them up. And there's an example of the struct field. So that's an array of struct fields. Normally you would see a struct type kind of as the outline of that. So there we go. We're going to back up the location. In case we screw something up, it's been known to happen. And then we're just going to, you see that code in the bottom, we're going to instantiate a schema migrator, that's the class that does this in the library. And we're going to say, hey, for all of the keys that I found in rescued data, one at a time, go through and add them as top-level fields. And again, I'm doing this top-level fields, I'm adding them, this is just for simplicity. The API covers arbitrarily nesting, so you don't have to do it like this at all. This is just an easy way to think about it. And now, this is a sanity check. Real quick, let me pause this. So since the schema migrator will have altered the schema that it loaded from the file, so remember, autoloader has a file, schema migrator read the file, you told it to mutate the schema in such a way that makes sense to you, right? You can see that here. And now what I'm doing is I'm creating a data frame with no data in it, but I'm specifying a schema. And the reason I do this is because if you somehow screw up the schema mutation, the struct type mutation, this will fail. Right? It'll be like, what are you doing? This is nothing. I can't do this. So it's always good. You always want to sanity check yourself, because in notebooks, it's way too easy to write code that sucks. Right? You want to make sure you test your code at least somehow. So doing some kind of an assertion or doing some kind of a sanity check, I think, is a good practice and pays in the long run. I'm going to swirl the mouse a little bit. There we go. So there you go. Migrator.override schema is going to be called after manually stopping the streaming job. So if this is Okta, I'm going to stop the Okta stream, for a minute. I'm going to run this. I'm going to turn it back on, right? Minute downtime at most. And then when it's done, you can see, so this is actually the file that Databricks writes. You can see once you look at the actual file, you'll find that there are now new items appended to the end. They'll always be at the end. So this was one of them. The virtual machine image name was a new key that we found from Drift Discovery. And there you go. It matches that. So now everything will be right as rain. Let's go back. OK, conclusion. Only use merge schema? No, not the way. Generally not the way. Autoloader rescue, some good old-fashioned elbow grease, and merge schema, oh yeah, that's the way. So summary, we can achieve schema drift detection across autoloader streaming data sources that support rescue, which are quite a few file types. We can create visualizations, dashboards, and alerts to help understand and assess the drift that we're seeing across all of our data sources for our enterprise. We can selectively decide which one of those keys we want to promote as first-class citizens or columns in our Delta table. And we can minimize the streaming ingest job downtime to just a few minutes, if that. So limitations, right? Don't let me fool you. Nothing's perfect. So the biggest limitation is going to be on the migration side. So obviously, the discovery piece, that's good. That'll work all day, every day, no problem. But the migration, since we're specifically modifying files that Databricks is creating, there's always a chance that they change what they're doing, and that's incompatible with what this is doing. So it is not wise to use this code on a new version of a Databricks runtime without first testing it, right? You should always test it, because if they decide to fundamentally change it, or maybe they change the version, that actually won't break it. But if they do something fundamentally different, that could break it. So you should know that before you do it. There's going to be a blog on this, so look for it on the Databricks website. I have 2 minutes left. Oh, man, we got to go fast. That's it. Thank you.